There are two more energy topics that I want to talk about, and this is not going to, neither one of these is going to take very long. And the first one is combination problems. So there are a lot of problems where you will use both conservation of momentum or any kind of momentum thing. I'm actually going to do an example with conservation of momentum, and I'm also going to do an example with the impulse momentum equation. But then these combination problems are they take that momentum thing, and then another part of the problem uses conservation of mechanical energy. So that's the first one I want to talk about. There's no new concepts that I'm going to bring up here. It's just a way to sort of how you go about kind of noticing that you're going to have to use more than one approach in one problem. So these are problems where you're going to have momentum and energy in the same problems. And then the second thing I want to bring up is, I brought this up when we did the derivative review, the calculus review, but the derivative relationship and how that works. So the relevant derivative relationship is that the force on an object along a line is equal to the negative derivative of the potential energy with respect to x. Okay, so the first thing I'm going to do is talk about these problems where you combine momentum and energy. And all you need to really know for this kind of problem is that, so there's going to be some kind of collision or impact, and you're going to use momentum for the impact part, and then you're going to use conservation of mechanical energy for the rest of the problem. So first, momentum is what you're going to use for the impact, and that's going to be a short duration impact, and you're only going to be using momentum for that small amount of time where that impact is taking place. And then you're going to use conservation of mechanical energy for the remainder of the problem. Okay, so for the first example, let's imagine that there is a 2 kilogram mass hanging from the ceiling. And a bullet is fired into that mass. And so this bullet is going to have a mass of 0.004 kilograms. And at the instant that it hits the hanging mass, it's going to be moving at 900 meters per second. When the bullet lodges into the mass, it's going to make this system swing. And so, the mass with the bullet inside is going to swing up to here. And we want to see what this change in height is. Okay, so this is what we want to calculate, how high that swings. And notice we're going to be using conservation of mechanical energy, which depends on the gravitational potential energy of this mass. And so what we're going to calculate is this change in height. We're not going to calculate like the total distance along this circular arc that it travels or anything like that. And this is related to the way that gun muzzle velocity used to be calculated before there was high-speed video and all that stuff. So this was actually something people did. They started with different things. What they wanted to calculate the speed of the bullet. And they did it by measuring the height that the mass swings, because that's a relatively easy thing to measure. And then they back calculated the speed, but we're doing it in this direction. Okay, so I'm going to start with the collision. And for the collision, we're going to use something related to momentum. In this case, we're going to use conservation of momentum. So before the collision, we have a mass of 0.004 times, well, notice for this, you always need to have a positive direction. I'm going to choose positive direction to the right. And so that 900 meters per second, the velocity is positive 900. And then we'll add that to the mass of 2 kilograms times the velocity of 0 before the collision. After the collision, this is an inelastic collision. The bullet is going to get stuck inside the block, and then at that point they're going to have the same velocity. And so the combined mass of the system is 2.004 kilograms, and we want to calculate this speed v. Okay, so we have, this term goes away. Divide both sides by 2.04, and we get that the velocity of the system after the collision is 1.80 meters per second. And now we have to deal with the swing. So what's happening with this swing? Let's think about a free body diagram of the block and the bullet during this swing. Okay. So there's a weight force acting down, that's 2.04 times 9.8. And then there's a cable force this way. In order to use conservation of mechanical energy, any non-conservative forces have to do no work on the system. Okay, well, this one's conservative, the weight, so that's good. We have a potential energy function for the weight. But now what about this cable tension? Well, that's not a conservative force. That's a non-conservative force. But notice that this mass is going to be swinging in a circular pattern. Okay? And that cable tension is toward the center of the circle. And so one of the things that we know is that if you have something in circular motion, any forces toward or away from the center of the circle do no work. And so this does no work. And so we can use conservation of mechanical energy for this system. Okay, so instant 1 is going to be immediately after the bullet lodges in the block. Instant 2 is going to be when it reaches its highest point. I'll say my y equals 0 is here. That's almost always my strategy, just put it at the lowest point. So the gravitational potential energy at instant 1, the y value is 0, so it's going to be 0. The kinetic energy is 1/2 times the mass, which is 2.004. Give myself a little more room. Times 1.80 squared. Okay, and so that kinetic energy comes out to be 3.25 joules. And then when it gets to its highest point, well, we don't know what that height is, but we're trying to calculate it. So it's equal to the mass times 9.8 times that y value. The kinetic energy when it reaches its highest point, it slows down as it goes up and it stops for an instant before it starts swinging back. So this is at the instant that it stopped, and so the kinetic energy is 0. Now put these into conservation of mechanical energy. You got 0 plus 3.25 is equal to 2.004 times 9.8 is 19.64, and then times y plus 0. Divide both sides by 19.64, and you get that final y value is 0.17 meters. For the second example, I'm going to do one where instead of using conservation of momentum, I'm going to use the impulse momentum equation. But besides that difference, the approach is the same. So let's say that we have at the bottom of a hill a cart with a mass of 0.5 kilogram. And there's a force applied for some time interval here. And I'm going to say that this force is 50 newtons, and it's applied for a duration of 0.1 seconds. And the question is, so that's going to speed it up some amount. The question is, how high up this hill are we going to get? So if it starts out here at what I'm going to call my y equals 0, and it gets up to a point here on the hill, what is this distance? What is this height? I'm going to use the impulse momentum equation for the 0.1 second impulse. So the first thing I'm going to do is just for that impulse, I'm going to use momentum. I'm going to calculate the speed of this cart after that 0.1 seconds. And then I'm going to use conservation of mechanical energy to figure out how high up the hill that speed takes it. Okay, the impulse momentum equation says the force, that's the average force. In this case, it's constant the whole time, so the average is that value, times the interval, the amount of time, is equal to the later momentum minus the earlier momentum. The later momentum is going to be 0.5 times whatever the velocity is. Based on the direction of my force, you can see that I'm choosing my positive to be to the right. So that's the momentum at the later instant, but before it gets to the hill. And then the earlier instant is 0.5 times 0. So this goes away. Divide both sides by 0.5, that's multiplying by 2, so you have 5 times 2, and the velocity is 10 meters per second. And now we're going to use conservation of mechanical energy to figure out, if you start at the bottom of the hill at a speed of 10 meters per second, how high up the hill do you get? So I'll break it up into instant 1 and instant 2. Instant 1 is right after that force has been applied for 1/10 of a second. Instant 2 is when it reaches its highest point up that hill. My y equals 0 is at the bottom of the hill. So y is equal to 0 at instant 1, and so that gravitational potential energy is 0. And the kinetic energy at instant 1 is 1/2 times the mass times the speed squared. And if you multiply that out, you get 25 joules. At instant 2, the gravitational potential energy is the mass times 9.8 times the height. And so that gives 4.9 y. And then the kinetic energy, well, when it reaches the highest point, the speed is going to be 0, which means the kinetic energy is going to be 0. And now we can put this into conservation of mechanical energy. 0 plus 25 is equal to 4.9 y plus 0. Divide both sides by 4.9, and you get the y is equal to 5.10 meters. So it's not telling you how far along the hill this travels, how far along the ramp. It's saying that just the difference in height is going to be 5.1 meters. Okay, and it doesn't matter what the shape of the hill is. Of course, it would matter if there's friction, and there's always friction, but as an approximation, assuming no friction, it doesn't matter what the shape of this ramp is. All that matters is the difference in heights. And then the last thing I want to talk about is the derivative relationship. I've mentioned this a few times before. I just want to point out that it's relevant here. And this derivative relationship says that the force as a function of x acting along a line is equal to the negative of the derivative with respect to x of the potential energy function. So if you have the potential energy function along a line, you can always use that to calculate the force. And so for this example, I'm going to use the idea of a nonlinear spring. This is a spring that behaves differently than the kinds that I've talked about so far. It's not an unusual idea. In fact, muscle tendons, ligaments behave like nonlinear springs. The linear in linear spring or nonlinear spring refers to the fact that when you look at the force applied by the kind of springs we've talked about, you're just multiplying negative k times x. Okay, and that's a linear relationship between the force and the x. In a nonlinear spring, you have a different, you could have a polynomial with an exponent different than 1, or you could have sine or cosine functions, exponential functions, anything that's just not multiplying by that variable itself. So let's say we have a system like this. And we have a cart. Let's say this cart has a mass of 0.4 kilograms. And I'm going to just draw something funny for this spring so to make it clear that this is not the kind of spring we've been using. And let's say that we know that the potential energy function for this spring has this form. The potential energy is equal to 100 x to the third plus 20 x squared. Okay? And what we want to do is first calculate the force as a function of x. Second, We want to use that to calculate the force when x is equal to, let's say, negative 0.05 meters. And then once we have that force, we want to use that to calculate the acceleration at that instant when x is equal to negative 0.05. Just to get some little more practice with the relationships between all of these things. Okay, so first, and this is really the derivative relationship, to calculate that force, let me say also, we're going to say that the positive direction is this way. And like with any kind of spring, we're going to assume that x equals 0 is when the spring is at its resting length. And so x tells you how far you are from the resting length in the positive or negative direction. The force as a function of x is equal to negative 300 x squared plus 40x. And it should be minus 40x because of the negative sign. Okay? And so that's the derivative relationship. If you have the potential energy function, you can always calculate the force function. Now we're going to plug in x equals negative 0.05 and calculate this f. So we're going to calculate f of negative 0.05. Plug in negative 0.05 to both of these, and you get an f value of positive 1.25 newtons. Now for the acceleration, and since we have a positive direction going to the right, this means that force at that instant is pointing to the right. And now for the acceleration, well, along this line, the only force is from that spring. You could see that if you drew a free body diagram. And so along this line, Newton's second law says 1.25 is equal to the mass times the acceleration. And so the acceleration is 0.5 meters per second squared. Since the force and acceleration are both positive, we know that they're going in this direction.